All right, y'all, so here we go with our first question with kinematics. Note that this is a level 1 question for AP Physics 1. That doesn't mean, level 1 doesn't mean easy. It just means that it's the easiest that you're likely to see on an AP exam. So here we go. We're going to try to use the equations that we just learned, figure out how to apply those in this situation. I'm going to talk you through it and show you some things that may help you as you go forward. All right, so we've got a light rail commuter train starting at rest that has a constant acceleration. It covers 50 meters in the first 8.60 seconds, and find the acceleration of the train. Just a couple of notes here. The first thing I want to mention is notice that this is 50.0, and you may be like, well, that's weird. Why is it 50.0? Well, because that means that it has been measured precisely to this place. So 50 meters with a dot would say it was measured correctly to the nearest meter. This is at least to the nearest decimeter. All right. Same thing with the 8.60 seconds. That means that it was measured precisely to hundredths of a second. And so that zero is what we call significant. It's important, or we wouldn't have written it down. So both of these numbers then have 3 significant figures. And so therefore, when I get to the end, my answer should have 3 significant figures. All right, so I'm going to write that down just to keep it in mind. The other thing is, when we're reading a question, always look for hidden information, right? The 50 meters and the 8.6 seconds is pretty straightforward. The fact that it's asking for the acceleration of the train is pretty straightforward. There's one little piece of hidden information here, which is where it says it starts at rest, where that's not given as a number, but we can use that information. Starts at rest means that our initial velocity is 0 meters per second. All right, or it could be kilometers per hour or whatever, but I'm going to try to keep this, since I've got meters and seconds, in SI units. Now, what I recommend doing here as you start to do these kinematics questions is create a table that has the 6 variables that we talked about: initial position, final position, initial velocity, final velocity, acceleration, and time. Now, this table could be the same for all 3 questions, or it might change depending on what my initial and final conditions are. Now, in this one, the initial and final conditions are after that 8.6 seconds. So I do have my time, which is 8.60 seconds. I've got that it covers 50 meters. So I don't have a specific starting position, but I do know that from the starting to the end, it has traveled a total distance of 50. So I'm going to go ahead and put 0 here, and then 50 for my final position. Now, you could put 100 here and 150, or 1,000,000 and 1,050,000. It really doesn't matter, as long as you end up having a difference of 50. Now, I encourage you to not believe me, right? I'm a new guy. You don't know me very well. I encourage you to try it out. See what happens in the end if you use different numbers here that have a difference. Remember, it has to have a difference of 50. All right. Then we got our initial velocity, which was 0 meters per second. And we are looking for the acceleration. So what I like to do is I like to write that variable there to remind me that that's what I'm looking for. That's important. Now, what you'll notice is that in that first question, I do not have anything about the final speed or the final velocity. I also am not looking for that, so I really don't care. So that's going to go away. I'm not going to put a V there. I'm not going to put anything there, because that might confuse me later and make me think that I want to or could solve for that. And actually, I can solve for it. I just really don't care about it right now. So here's where kinematics gets us to start thinking a little bit critically, because yes, there are 3 equations, and actually 2 of these are useful right now, but one of them is better than the other, right? I could solve for the final velocity, but I don't need to. What I want is the equation that has x naught, x, v naught, a, and t, and that does not have v in it. Do you see one? I do, Mr. Bywater, I do. Me. Thank you, high-pitched voice in the back of the classroom. I think you should choose this one. All right, very good. So that is the only equation that doesn't have v in it, right? This is v. Notice that we do have the little subscript x's on a lot of these. That's not really super important right now, because right now we're only doing one-dimensional motion. That'll become a little bit more important. This is the way it's written on your AP exam. That'll be a little more important when we start to look at motion that has both horizontal and vertical components. But for now, we're not there. We're just going to do one-dimensional kinematics. So therefore, we're going to use this equation right here. We're going to say x equals x naught plus v naught t. Notice that as I'm writing it down, I'm not bothering to put that subscript x there because it's only one direction. I don't need to remind myself of that. Then I can just go ahead and put in the numbers. As I put in the numbers, because I'm already in meters and meters per second, seconds, I'm all of my numbers, all of my data is in SI units. And so I don't really need to worry about putting the units into my problem. If you use units other than SI, I recommend that you actually put the units into your problem to make sure that you end up getting at the end proper units. All right, so I got my 8.60 seconds. Obviously, I don't really need to write this. A lot of times you'll just be able to say, oh, that's 0. Oh, this is 0, so that's going to be 0. And we end up with just that 1/2 a and then the t squared. All right, now from this point, it's not even physics anymore, right? This is just algebra at this point. And so we should just be able to take that 50, divide by the 1/2, and then divide by 8.6 squared, and we get 1.35. So I get an acceleration of 1.35. Now it does go on, but that being the case, I actually don't need to use all those digits. I'm going to do my answer in 3 significant figures, which is that 1.35 meters per second squared. I'm not going to do 1.4. I'm not going to round it up. I'm not going to use more digits. I'm going to use just the 3 significant figures from the information that was given in the beginning. All right, so there you go. That was pretty straightforward for part A. Let's move on to part B. Now in part B, it says, knowing the acceleration of the commuter train from part A, so yes, we do, how long does it take to reach its top speed of 80 kilometers per hour starting from rest? All right, now this is asking how long. So this is not going to be the same conditions as before, right? My distances won't be the same. My time won't be the same. My initial velocity, it does still say starting from rest, so that's going to be helpful. Let's go ahead and make our table here. And so we got x naught, x, v naught, v, a, and t. Our initial position, we're going to call that 0 again. It doesn't really give me anything about distance here, so I'm going to hopefully skip that. I've got my 0 meters per second there. Now, the final velocity does give me how long does it take to reach the top speed of 80 kilometers per hour. I don't really want it in 80 kilometers per hour, so I'm going to go here and I'm going to do some conversions. I'm going to use my dimensional analysis here. So 80 kilometers in 1 hour. I'm going to turn the kilometers into meters while getting the kilometers to cancel out. I know that 1 kilometer is 1,000 meters, so that gets rid of my kilometers. Now I'm going to turn my hours. You can go straight to seconds if you want, or if you don't know how many seconds are in an hour, you can go from hours to minutes. I want the hours to cancel out, so I know 1 hour has 60 minutes. And then I want to go from minutes to seconds, and I want the minutes to cancel out. And so 1 minute is 60 seconds. And so now I should just be able to take that, and I'll go 80 times 1,000 divided by 60, and then divided by another 60, divide by everything on the bottom there, and we get 22.2. So my final velocity there is 22.2 meters per second. All right, now we're ready. We got the acceleration from the previous part, which is 1.35 meters per second squared. And the question is, how long does it take? So I'm looking for t. Recognize I didn't have the x, and I don't need the x, so therefore I'm going to get rid of that one. I'm going to choose the equation that does not have x in it. Okay, so this one has x, I don't want that one. This one has x, I don't want that one. So I'm going to go with this equation this time. Okay, now I could probably get there eventually by using the other equations. But again, part of our introductory unit here is getting used to thinking in a way that's going to be the most efficient. right? Not just what will work, but what's the best way to accomplish this. All right, so we're going to go with this equation. We'll put our final speed in there, the 22.2, our initial velocity, and the acceleration of 1.35, and time. And so then we should just be able to take that number, divide by the 1.35, and we get 16.5 seconds. Notice again that I've used three significant figures because everything that I used to get the acceleration had 3, and the new information also had 3. Now, you may wonder about this 0. Well, I put a 0 in there. Well, isn't that one significant figure? No, because I know exactly where that is, right? That is at 0.00000 meters. I'm defining that as 0. Same thing with the initial velocity here. It may look like one significant figure, but I'm defining that velocity as at rest. And at rest is 0.00. So that actually has an infinite number of significant figures there. All right, so just to make sure that you're not too confused with that and that everybody's on the same page, quite literally. All right, moving on to part C. So part C says vehicles are often rated depending on how far they travel when acceleration from 0 to 60 miles per hour. Using the, oh, that is bad English, but I really don't care, accelerating from 0 to 60 miles per hour. Use the acceleration found in part A, determine the distance the train travels as it increases from 0 to 26.8 meters per second. All right, so we're going to make a new table. It's asking it to determine a distance. It's going from 0 to 60. That's a different speed, so very, different things going on here. So definitely a different situation. So I'm going to remake my table here. And it does say using the acceleration found in part A. So we're going to use that 1.35 meters per second squared, again, still in SI. Determine the distance. So I'm looking for this. I'm going to put an X there to remind me that that's what I'm looking for. And then it goes from 0 to 60, and I did already do that conversion for you. So the 26.8 meters per second. That's meters per second. The easiest way to do this is just to make that 0, because then I go from 0 to x, and when I solve for x, that is the distance from 0. That would be the distance the train has traveled. So you'll notice in this one I don't need time, and so when I look at my equations, the first two have time in them. I'd really like to avoid that because I don't have it and I don't need it, so I really don't care about time. So let's use this last equation here. We'll go v squared equals v naught squared plus 2ax minus x naught. So v, we'll put in the 26.8 squared equals 0 squared plus 2 times 1.35 times x minus 0. Of course, that's going to be 0. Now, again, not physics anymore. This is just straight up algebra. So we'll go that 26.8. We'll square that. Then we'll divide by 2. We'll divide by the 1.35. And so we end up getting 266. Again, everything's in 3 significant figures. So I'm going to go 266 is x. And because I use SI units for all of these, my final answer should be in SI units. Notice that it was x minus 0, so I don't really need to worry about the 0, and I get my final answer of 266. So there you go. That's a level 1 question. Notice that it's mostly just putting numbers in and doing the algebra, and that's really it. So that is a pretty straightforward question. Why don't you come along with me and we'll try something a little more challenging. Let's go.